I please Professor Joachim Mnich, Director for Research and Computing, to give his explanation, his speech, and so here.
Okay. Yeah, very good. It works. Yeah, thank you very much. I have the pleasure to give you an introduction to CERN. For those of you who are not physicists, I have very good news. This is one of my few talks which do not contain a single formula of physics, which usually is not the case. So, CERN, let me start where we are. You see here a picture, an aerial picture of the area. You see the Lake Geneva, you see the airport there, and you see this big circle of 27 kilometers circumference, which is the LHC, the Large Hadron Collider, our flagship project. So CERN is the biggest laboratory for particle physics, and our goal is to understand the most fundamental particles and laws of the universe. Actually, our mission is underpinned by 4 pillars. Obviously, research is one of them, but we also are very strong and have very strong activities in education and training, in collaboration, and of course in technology and innovation. And I will briefly go through all these 4 pillars. So let me start with research. This is a picture during the construction of the Atlas detector. It's almost 20 years old, this picture. And I think looking at this gentleman there, you get an idea of the size of this detector. Now it is filled, it's completely filled with high-tech detectors used by the experiment. So what we are studying is actually what the universe is made of. And you see here on one slide our current understanding on how matter is composed. So you know that matter is composed of atoms, a nucleus which is surrounded by a cloud of electrons. The nucleus itself consists of particles called protons and neutrons. And today we know that even these protons and neutrons are not elementary particles, but they are themselves composed by quarks, as they're called. And quarks, that what we know today, is that their diameter is less than 10 to the minus 18, maybe 10 to the minus 19 meter as now. So in other words, if nanotechnology is 10 to the minus 9 meter, we are doing something like nanosquare in this sense. Now the interesting thing that has appeared over the last 50, 60 years is that studying these fundamental building blocks of matter gives you also some insight into the development of our universe. You see here again cast on one page how we understand today the development of today's of the universe. The universe has an age of about 14 billion years, and looking from here, the right side, that what you see can observe is the universe as it is today by telescope and other astronomical means. You can look into the past by looking at very distant galaxies, for instance, but there is a barrier here at about 380,000 years after the Big Bang, which you cannot access through light. And that's where we come in play. With big accelerators like the LHC, we can reproduce conditions of the universe a tiny fraction after the Big Bang. So if you wish, we look at the development of the universe from both sides, from the right through astronomical means and from the left by accelerators as the ones we have at CERN. So at CERN, we tried to help answer these questions. We have several Nobel Prize winners, as you see here. Carlo Rubbia for his contribution to physics and research, Simon van der Meer for accelerator technology, and George Sharpak who made enormous contributions to the development of detectors. And this are, if you wish, the newest kids on the block. The discovery of the Higgs boson 10 years ago was awarded the Nobel Prize then the year after to Peter Higgs and François Englert, who almost 50 years after they had the idea of the Higgs mechanism finally got the prize, because we at CERN could prove that they were right. Now, in order to do this research, the important thing that we are doing at CERN, together with our collaborators all around the world, is to develop technologies. And we develop technologies in 3 key areas. Obviously, in particle physics, in particle accelerators, but also in particle detectors, and not to forget is the computing technology, which is also very important for our research. Actually, if you look at the CERN personnel, there are many more people working on the advancement and the development of these technologies than on research questions. I mentioned already the Large Hadron Collider, our flagship project, 27 kilometers in circumference. It's about 100 meter underground. So you have here sort of an artistic view inside. Then what we do there is we have a beam of protons going in one direction, a beam of protons going into the other direction. They are held on their circular trajectory by the strongest magnets possible, superconducting magnets. And inside this ring, the particles are accelerated close to the speed of light. I'm often asked what means close to the speed of light, and I sat down the other day and calculated what it actually means, and I put it in here in percent. So in practical terms, it is the speed of light that we are talking about. Now, these 2 particle beams are then brought into collision at 4 points. And at these 4 points, we have the 4 experiments, the 4 big detectors. ATLAS, CMS here, which are the biggest ones, the so-called multi-purpose experiments, because they're supposed to cover a very broad range of the possible physics that we can do at the LHC. And we have 2 more specialized experiments, which are called ALICE and LHC-B, which are also shown here. Now, what do we do at the LHC? As I said, we bring particles into collisions, protons, sometimes also heavy ions, and we do that for the protons about 1 billion times a second. For instance, at ATLAS or CMS, we produce 1 billion proton-proton collisions a second. Now, if I look carefully at this, it's probably now more close to 2 billion collisions per second that the accelerator is able to produce. And this energy of the particles is then converted into new particles. And you see here one of the pictures where this we interpret as the production of one Higgs boson. And the trace of the Higgs boson are here, these 2 green beams that you see here, representing 2 photons into which this particular Higgs boson has decayed. Now, these detectors can be imagined as 3D cameras. So these detectors measure energy, direction of the particles. They take, as compared to your camera that you have on your mobile phone, they take 40 million pictures a second. That, I think, makes them also a bit more expensive than a normal camera. And I think the important things to notice here is that these detectors have not been built by CERN, but they have been built in large international collaborations. ATLAS, for instance, more than 240 institutes from all over the world. I think it's close to 50 different countries now. And CERN, in these detectors, we are just one partner among the 240. Very important, as I said already, is computing, and it has been realized very early when designing the LHC and the experiment that the amount of data which is produced in this collision is too much for a single computing center. And that was the birth of the worldwide LHC computing grid called WLCG. And you see here a picture of the traffic of the data. So these WLCG has now about 1 million or so of processing computers in 170 data centers, and again, more than 40 countries here. And if you ask me, this is sort of the predecessor of what is now called cloud computing, which is a multi-billion-dollar or euro business worldwide. Now, this was about the LHC, but I think it's also important to mention that we have a much broader program that would be called diversity program in science, which includes nuclear physics, Isolde and Entov. It includes antimatter research, cosmic ray and cloud formation. We have fixed target experiments which are suitable to investigate very, very rare processes, and we do also contribute and we act as a platform for European contribution to the neutrino experiment LBNF Dune in the US. Okay, that's it. Now, sometimes we are asked, no, you have discovered the Higgs, are you done now with your field? No, this is not true. We still have very fundamental, important and very fundamental unanswered questions. And here there are only a few examples of this. Now, it's a bit embarrassing for particle physicists like me to admit, actually, we understand only 5% of that, what is around in the universe. 95% of the mass and the energy of the universe doesn't fit into the picture that we have developed over the years. So there, we believe there is many, many more things to be discovered. We have this question, which I find in particular intriguing, is the question why we can exist at all. So, shortly after the Big Bang that we know today, there was a big annihilation of matter and antimatter. And only 1 out of 1 billion matter, that's what we call matter today, particles survived. And the question is, why is that? So there are 2 answers to this. Answer number 1 is somebody put in a little bit more of matter into the soup. This is a boring explanation for scientists because there is not much research we could do about that. The other potential answer, and that's where we're after, is that matter and antimatter are not ideal mirror images of each other. There is a mechanism which took care that a little bit of matter at the end could survive this big annihilation of the Big Bang. And that's what you are made of, I'm made of, everything that surrounds us is made of. We have the question about the Higgs. Higgs is a very special particle, and we are just beginning to understand a bit about this. And the last example that I want to mention here is about gravity. The first force that we all experienced in life is something, again, that we do not understand, and something which do not fit into our picture of today. So what are we planning at CERN in order to shed a bit more light on these questions? So the next big step actually will be what we call the high luminosity LHC. For the non-expert, luminosity is just the scientific word for the number of proton-proton collisions per second. And in this upgrade, we want to increase this rate by up to a factor of 10. So 10 times more collisions, proton-proton collisions that we have now. Why do we do that? Because it will give access to even more rare processes which are there. Dark matter is supposed to be the origin of such very rare processes. It will give greater precision to the measurements that we can do already now, and also help us, hopefully, to discover new things. We will start this in 2029 and then run until approximately 2040. So this is a program for about 20 more years to come. What are then the scientific priorities for the future? So these priorities have been defined 2 years ago in a process which was under the auspice of the CERN Council, namely the update of the European Strategy for Particle Physics, and it very clearly gives the priorities for the coming years. So number one priority is the LHC and the high luminosity phase, which I just introduced to you, to fully exploit the scientific potential. The next one is to build, after the LHC, a so-called Higgs factory, to understand this mysterious particle a bit better, because we think it might be a door to understand more about some of the fundamental questions that I just mentioned. And in order to do so, and also to see what could be then a follow-up project of the LHC to reach even higher energies, we have started at CERN to investigate the technical, but also, of course, financial feasibility of a future collider, the so-called FCC, Future Circular Collider. And this is one slide on this project, this so-called feasibility study. What we have in mind is to try to see how about a 90-kilometer circular collider could fit into the Geneva area. You see here, this is, in this sketch, the Lake Geneva. This is the LHC here, and that's how an FCC 90-kilometer ring would fit into the landscape here. The idea is to have a two-stage project then at the end. It's, by the way, very similar to what we had in the past with LEP. In the current LHC tunnel was an E+, E- collider, which was then, and in the year around 2000, replaced by the LHC as a Hadron collider. So again, here we think that the first stage should be, following the European strategy, a Higgs factory, electron-positron collider, which would have the capabilities to produce enormous amounts of Higgs events, but also top quark, W, Z, and so on and so forth. And then in a second stage, it would be then also in the second half of this century, not earlier than that, a proton-proton collider with collision energies of, say, around 100 TeV, which is a factor 7 more than the capacity of the LHC as of today. And you see here a bit of the planning that is being made as part of this study here. That much to research. Now let's move to collaboration. Now, CERN was founded 68 years ago under the theme Science for Peace. 1954, actually in the aftermath of the Second World War, by 12 European member states. Today, we have about twice as many, 23, among them, as you know, certainly the Czech and the Slovak Republic. There are associate member states in the so-called pre-stage to membership. So there are 3 countries who essentially applied for the membership. There are also associate members and there are observers. And not to forget, there are around 50 countries and territories with which we do have collaboration agreements, and you see them all listed here. The annual budget of CERN is about 1.2 billion Swiss francs, which is to put that number into perspective, about the budget of a medium-sized European university. And we have, if you count everything here together, say about 3,500 employees, staff, and fellows. But the important number, I think, is the one below here. That what is called in the CERN terminus associates are the scientists and what we call also users and other people which do their research at CERN. And if you add them together, it's about 13,000. So all in all, the whole CERN family consists of about 16,000 scientists all around the world. It is indeed a laboratory for people around the world that you see here. If you now take this 16,000 people, you see that less than half of them are actually from member states. You see there is a lot also from observer states and from non-member states. If you, for instance, just for comparison, see that about 1,800 researchers from the United States are performing their research at CERN. And I give you here also the numbers, the latest numbers that I got for the Czech Republic and for Slovakia. And you see that there are 200 researchers from the Czech Republic, more than 100 from Slovakia are doing their research at CERN. And there is also some 20 or so people from each country, member of the CERN personnel. CERN, I think, is also a model for an open and inclusive collaboration. There are many examples like this. The CERN, the experiments that we do, for instance, at the LHC, I think are a very good example of that. Having in Atlas 3,500 researchers from all over the world contributing to one project, I think is without example elsewhere. Sesame is a synchrotron light source in Jordan, in the Middle East, with members from many Middle East countries, also those which are countries which are not, which do not have the best political relations to each other. But Sesame actually has been founded according to the model of CERN, and we're doing also a lot of support, infrastructure support. Like one example is the support that we do for the United Nations, because we house the IT infrastructure for their satellite analysis technology for emergency responses after disasters, for instance. Technology and innovation. Now, I guess most of you know that the World Wide Web has been invented at CERN more than 30 years ago in order to help the researchers distributed all over the world to work very efficiently together in the experiments. But this is just one out of many examples, and there are many more in medical imaging, cancer therapy, material science, and so on and so forth. I have a few examples here where we see how technology that has been developed at CERN together with our partners, the universities and laboratories around the world. Accelerators, just to give you one example, I mean, a very small fraction of the accelerators which have been built in the world are for research, are for particle physics research. Most of them are now in hospitals for cancer treatment. There are in industry for lithography, for instance, to produce semiconductors with very, very low structure sizes. There has been more than 30 years, almost 40 years ago, development of crystals to detect particles at CERN and to measure their energy. These crystals are now used in positron emission tomography, which is general used now for medical imaging and diagnostics. We have so-called pixel detectors have been developed for the LHC experiments, for Atlas and CMS, and they are now used for X-ray imaging. This is from a company that is working together with CERN, which have further developed this technology. And you see here an X-ray image of a wrist and the Swiss watch. I'm sure this is a Swiss watch, which is pictured there. We are also doing, with our accelerators now, the production of very special radioisotopes, which are used, again, in nuclear medicine for research, therapy, and also diagnostic. Education and training. Now, this plot is one which I particularly like. It shows the age distribution of the 16,000 people working at CERN. And you see here this clear peak, maximum at 27 years, and then it extends until, say, around 35. These are PhD students, and these are postdocs, young researchers. And then you see also on the other end that there are still people at a very high age working occasionally, at least, at CERN. And one thing which I realized when looking at this plot yesterday, I think this plot has to be extended until 100. I know at least of one case which would fall out here. Now, what are the people doing, in particular the young people, the ones in this peak here? And what you see here is that about half of them, almost half of them, at the end of their stay at CERN, in the CERN experiments, they go to industry. They bring their knowledge on technology that they have developed at CERN in the experiments, for instance, into industry. They do go to governments and other organizations. And only about 1/3 stays in academia. Not necessarily in particle physics, but also in other science fields. I think this is a very, interesting plot. What are we doing for training and education is also a lot. We have, at any moment in time, about 3,000 PhD students. So there are 3,000 young people around the globe which are doing at this moment their PhD work with the experiments that we are performing at CERN, with experiments or with technology, of course. We have more than 1,000 fellows, technical, doctoral students. We have a teachers program, which for the last almost 25 years had more than 13,000 teachers from essentially Europe came to us to learn a bit about particle physics and to distribute this then in their classes. We have pre-COVID, of course, this went down to essentially zero during the pandemic, but before the pandemic, we had about 150,000 visitors on site every year. And this number is limited by our capacity, and that's why we will increase this capacity. I have here also for you the number from the Czech Republic and from Slovakia. You see that your countries are actually very actively participating in these education programs. Science Gateway, I mentioned this, for those of you who would come to CERN these days would almost see it like this already. Science Gateway is supposed to be our new education and outreach center. We will open it next summer in 23, and with that we hope that will increase the capacity for users in order to meet the demand then. Now, to conclude, a few words on the participation of the Czech Republic. I can be short here because I think we will learn in the following talks much more details about the participation. Here, you see here the universities that are contributing to the experiments. You see here high-ranking visit, the Senate Vice President visiting CERN together with my colleague Charlotte Vara-Kaule, who is the Director for International Research, for International Relations, at CERN. This is the involvement in 3 of the major LHC experiments, but also beyond that, the Czech involvement in fixed target experiment and also in one of the anti-proton experiments here. And I should not forget to mention that you're also contributing to the worldwide LHC computing grid here by housing one of the high-performance Tier 2 centers, which is in operation here in Prague, which is also a highly estimated contribution to the CERN program. Is not only, as I said already before, not only limited to, say, academic contribution, but also, and I think the Czech Republic is very successful here, in also industrial contribution to the CERN program. Here you see a few examples of this high-tech sector, the contributions on ultra-high vacuum technology from your country, scintillators for the LHCb spaghetti calorimeter was produced here in the country. But also interesting thing like using detectors, which is called Timepics technology, to unravel secrets of paintings. So a lost painting from Raphael, for instance, was identified using this technology here. A few words on Slovakia. Also here you see 6 universities contributing to the research. The president of the Slovak Republic visited 10 years ago CERN. You see here a picture of that visit. Also, Slovakia is contributing to 2 of the big LHC experiments, Alice and Atlas in this case, and to one of the fixed target experiment and nuclear physics as well. And also Slovakia is very successful in contributing through industry cooperation to CERN. Again, you see few examples of key contribution of Slovak industry to CERN, cryostat for some of the LHC magnets here, robots carrying LHC magnet, and even a prestigious industry award was won. And also taking very actively part in knowledge transfer and knowledge and technology transfer. Okay, I think my time is over here, and I hope I could convince you a little bit about what CERN is doing and convince you that we will also in future play a crucial role in the journey of exploration to some of them, which I still find most intriguing and thrilling fundamental questions that we have. Thank you very much for your attention.